Today we will discuss close packing in crystals. In crystals, how these particles are arranged very close to each other. When we discuss this close packing, we have to see the arrangement of particles in 1 dimension, 2 dimension, and 3 dimension. Arrangement of particle in 1 dimension or close packing in 1 dimension. Only one possibility is there. All the particles are arranged in a single line. Linear arrangement, that is only possible. Here one particle is touching the other. So they are very close to each other. So here you can see this particle is touching two other particles. So the coordination number is 2. What is coordination number? This is the number of particles which is in direct contact with the one particle. That is coordination number. So here coordination number is 2. So in order to understand 1 dimensional, 2 dimensional close packing, here you can see a video.
Close packing in solids. In 1 dimension, there is only one way of arrangement of spheres. They are arranged in a row and touching each other. Thus, the coordination number is 2. Packing in 2 dimensions. There are 2 ways of packing are possible in 2 dimensions. They are square close packing and hexagonal close packing. Square close packing. In this, spheres of second row are exactly above those of the first row. These spheres are horizontally and vertically aligned. In this arrangement, each sphere is in contact with 4 of its neighbors. Thus, coordination number is 4. 4 spheres come on the corners of a square, and this type of packing is called square close packing. Hexagonal close packing in 2 dimensions. In this, spheres of second row fit in the depression of the first row. First and third rows are vertically aligned. Each sphere is in contact with 6 of its neighbors. Thus, coordination number is 6. Centers of 6 adjacent spheres are at corners of regular hexagon. This type of packing in 2 dimensions is called hexagonal close packing. In this layer, there are some voids. These are triangular in shape. The triangular voids are of 2 different types. In 1 row, the apex of triangles are pointed upwards, and in the next layer, downwards.
So here, vertical and horizontal alignment, you can see. When you consider one particle, the centers of the adjacent particles, when it is joined, you will get a square. So it is square close packing, and it is hexagonal close packing. When you compare these two, which is more efficient packing, this one, hexagonal close packing 2 dimensional is more efficient when you compare the free space. The free space is known as void. Here the free spaces or voids are very small, but here the voids are very big. From this it is very clear 2 dimensional hexagonal close packing is more efficient. So when we think about 3 dimensional close packing, surely the arrangement of crystals will be above this hexagonal close packing. Which are the different possibilities in 3 dimensions that we can see. Here, square close packing. The first layer is square close packing. As we already mentioned, it is not an efficient packing. And above this layer, another layer is arranged, another layer is arranged, another layer is arranged, but you can see the spheres are exactly above the spheres of the first layer. So here, the second layer is exactly like first layer, or the third layer is exactly like second layer. Therefore, what is the arrangement? A type arrangement. And when you take the smallest repeating unit or unit cell, you can identify it as simple cubic unit cell. We cannot say it as a close packed arrangement. Simple cubic is not a close packed arrangement. For close packed arrangement, the first layer should be hexagonal close packing 2-dimensional. That we can see next. This hexagonal close packing 2-dimensional, but here 2 layers are shown. A faded set of spheres you can see, and that we can consider as the first layer. The first layer, as observed in the video, you can see some voids pointing upwards and some voids pointing downwards. Here it is described as O and T. And the second layer spheres are placed over the voids T. Can you see it? So here also the second layer voids are placed on, the spheres are placed on the voids T. Here the void, this void that is extending from the first layer, it is not covered in the second layer. This void is present in the first layer, at the same time it is not covered in the second layer. That means this void is common for first and second layers. Such voids are represented as O in this figure, and O represent octahedral voids. 2 types of voids are present after the second layer, after placing the second layer of spheres. So when you place a third layer, you have 2 chances, or you have 2 choices. Either you can place the spheres on tetrahedral voids, or you can place the spheres on octahedral void. If you are placing the spheres on tetrahedral void, you see the third layer sphere will be exactly above the sphere of the first layer. The third layer sphere will be exactly above the sphere of the first layer. Therefore, third layer will be a replica of the first layer, or that will be exactly like first layer. If you name first layer as A, second layer as B, and the third layer will be again A. So you will get the AB type arrangement. Another possibility, when you place third layer of spheres, you can place it over octahedral void. If you place a sphere over this octahedral void, it is not above the sphere of the first layer, it is not above the sphere of the second layer. Therefore, we can say we will get an entirely different third layer, which is not same as the first layer, it is not same as the second layer, but it is a different layer. So you have to represent the third layer using a different letter. So first layer, if it is A, second layer it will be B, and third layer it will be ABC. You will get an ABC type arrangement, and this ABC type arrangement results in another type of cubic close packing, another type of 3-dimensional close packing that is known as cubic close packed arrangement. Here hexagonal close packing, first and third layers are equivalent, second and fourth layers are equivalent, therefore AB type arrangement. This brown sphere is, when you consider this brown sphere and this brown sphere, they are exactly above. This blue sphere and this blue sphere, they are exactly above. But the second layer is different from first layer. That is hexagonal close packing, 3-dimensional. It is cubic close packing. The first and fourth layers are identical. Second layer is different, third layer is different. That is cubic close packing. Now placing the third layer of the second layer, that we discussed here, covering tetrahedral voids. When you place the third layer of spheres by covering the tetrahedral void, you will get AB type pattern, and this structure is called hexagonal close packed structure. And if you are placing the spheres over octahedral void, you will get a ABC type arrangement, and that is cubic close packing. And here one more thing that you have to listen. Both these types of close packing are highly efficient, and is 74% efficient. its packing efficiency is 74%. What is packing efficiency? That we can see in another class. Now we can go to the summary of this topic. What is it? In two-dimensional hexagonal close packing, there are voids. The second layer is prepared by placing spheres on the voids. After placing the second layer, two types of voids appear: octahedral voids and tetrahedral void. If the third layer is formed by placing spheres on tetrahedral voids, AB type arrangement forms, which is known as hexagonal close packing or HCP, three-dimensional. If the third layer is formed by placing spheres on octahedral voids, ABC type arrangement forms, which is known as cubic close packing, CCP, three-dimensional. Now, what is the coordination number of this arrangement? Here it is given as 12. How it will be told? You may remember in hexagonal close packing two-dimensional, one sphere is in direct contact with the 6 other spheres. Its coordination number is 6. Do you remember it? That means one sphere in a layer is in contact with the 6 spheres of the same layer, and it will be touching 3 spheres above it. That means 3 spheres in the second layer, and it will be in touch with the 3 spheres below it. That means a layer below that particular layer. So total how many? 3 plus 6 plus 3, total 12. Coordination number of HCP is 12. Similar the case of CCP. Coordination number of CCP also 12. Now what is the unit cell? This is a close packed arrangement. In a crystal there is a unit cell. What is the unit cell of HCP? That is hexagonal primitive or simple hexagonal. What is the unit cell of CCP? That is face-centered cubic. You can see the diagrams here. It is hexagonal primitive or simple primitive. It is face-centered unit cell. Particles are present at the corners and also at the center of each face. So today I stop here, and in the next class we can see the different types of voids and the problems related to hexagonal close packing and cubic close packing arrangements. Thank you.